Okay, now we go to the first subtopic, which is the Schrödinger equation in 3 dimensions. Alright, so we have been introduced to this complicated look of the Schrödinger equation. So from the previous chapter, this is a general one-dimension Schrödinger equation. So from there, actually we have here is a wave function, right? This is so this part is kinetic energy, and this part is potential energy, and this is total energy part. All right. So in the 3 dimension of, for example, if we consider a particle when it is moved in a space, so it can have 3-dimension component. Okay, so it can have a x, y, and z, so that it has a momentum in every direction. Pz. So since if it has a momentum in 3 dimension, so that it also have a kinetic energy, because kinetic energy depends on the momentum and also the velocity of the particle, right? So we can express the kinetic energy in 3 separate components in x, y, and z direction. So that we have to modify this one-dimensional Schrödinger equation into 3 dimensions. So what we have to do is that, so since this is for 1 dimension, we have to include 3-dimension wave function x, so x, y, and z, and the time. So we have 3 dimension and 1 time, right? So this is the new variables inside the wave function, and also we have a kinetic energy in 3 dimension. So therefore we see here, this is the difference. And then what else is that, because this is for kx, this is for ky, this is for kz. So the partial derivative is with respect to each component, x, y, and z. So that is for the first part of the Schrödinger equation for kinetic energy. And then for potential energy, also we have potential in y and z, So you see there is a change here, and also we have to include here also for y and z. For the right side also, make sure we have to include here x and y and z, and then there is no change to the time dependent. Alright, so this is called a general 3-dimension Schrödinger equation. So 3-dimension Schrödinger equation. So so that we just need to extend a little bit from our previous chapter to include another 2 dimension, which is y and z. Alright, so for the normalization condition in the previous chapter, in 1 dimension, right, it is written as dx equal to 1. That means the probability to find a particle along x-axis is equal to 1. But in 3 dimension, we have to change this x and include y and z. So this is 1 dimension. So because 3 dimension is a space, so it is a volume, right? We have to consider a volume of a space. So that we have v, this is volume. So in a small area of volume, we have to consider dv. So that is the change in here and here. So that is the normalization condition in 3 dimensions. So that is the thing that you have to extend from our previous chapter in 1 dimension. So later on, about the wave function, in previous wave function, we can separate the space x and time into two different wave function. Okay, two different function. That means the wave function is just a multiplication of the space and time component. Alright, so similar to three dimensions, we just include y and z. So y and z, and there is no change here. Okay, so this is a time-dependent wave function for a state of definite energy or stationary state. Okay, stationary state ataupun definite energy lah. Okay, so definite energy maknanya pada tenaga yang tertentu, so tenaga E lah. Jadi perbezaan dia hanyalah apa? Kalau consider daripada one dimension kepada three dimension, ialah kita ubah bahagian yang ni. Okay, so in a stationary state, which is a state of definite energy and the probability distribution is stationary, maksudnya dalam satu keadaan di mana tenaga tak berubah dan dia mempunyai sistem tu mempunyai tenaga yang tertentu. Oleh sebab dia mempunyai tenaga yang tertentu, maka probability untuk kita menemui satu zarah tu pada satu tempat tu ialah sama. Okay, maknanya contohnya dalam satu box ni. Okay, so keberangkilan untuk bertemu dekat sini tidak berubah dengan masa. Maknanya contohnya probability kat sini 0.5. Contohnya 0.5. Okay, kat sini 0.1, kat sini 0.1. Normalization condition menghendakkan supaya semua probability ni akan bersama dengan 1 lah. Bersama dengan 1. Okay, dan dia mesti sama dengan 1 lah. Forever sama dengan 1. Cumanya stationary ni maksudnya sepanjang masa kita probability untuk menemui pada kedudukan ialah 0.5 sahaja. Maknanya tidak berubah probability ni. Maknanya 50% chance to get the particle here. In case of dia berubah-ubah, in case the probability change, so it is not a stationary ataupun it is not a stationary state. So itu kita actually we are not considering that case lah in this physics modern syllabus. It is in the advanced level. In the advanced level, there is a case where it is not a stationary state because of the perturbation or the gangguan daripada luar lah, yang menyebabkan keadaan tu tak stationary, berubah-ubah dia punya probability. So just consider the stationary state means that it is a state of definite energy, so it has a state of energy E, and then the probability distribution is stationary, maknanya is not changed with time. Alright, so by considering that stationary state, so we can change from the time independent Schrödinger equation, which is in the stationary state. So we can transform from time independent Schrödinger equation into the time independent Schrödinger equation, but 3D. So 3D time independent Schrödinger equation. Panjang lah. Okay, type 3 dimension. Time dependent, maknanya kita abaikan perubahan the change in the state of the system. Okay, so previously we have learned about this time independent Schrödinger equation. We are no longer have IH over some dt, right? Kita tak ada dah ni, but because the state is stationary. So when it is stationary, it has a fixed energy. Alright, so we want to extend into 3 dimension. What we have to do is that we include this y and z direction. So we have to change because this is our new wave function. So this is our new wave function. We have to include that into this equation so that we have to modify. So this is the modification, plug, and then we have to include this partial derivative with respect to that y and z. Right, so and then this is also, you include another y and z. This is also y and z, and then this also y and z. So those are the difference between 1 dimension and 3 dimension. For the normalization condition, for a stationary state, we use this. So again, you have to differentiate this symbol. This this symbol. So it looks same, but it's not. Okay, so this include a space and time, but this is independent of time. So it is separated into two components. Okay, so the normalization condition, which is the probability to find a particle in a region, must be equal to 1. This is for 1 dimension. Now we have to consider 3 dimension. That means we have to include this y and z. And then there is the volume. So not only for x dimension, that it is for a volume of a space. Okay, this is the change. So you have change from 1 dimension to 3 dimension, 1 dimension to 3 dimension, 1 dimension to 3 dimension. So you have to make sure what change in those equation. Alright, so why you want to do that? Okay, so we want to understand an atom in this chapter. So what we will do is actually we have to set up the Schrödinger equation in 3 dimensions. In the next subtopic, we will apply each for a particle in a box. So we are going to the step. So step 1, we want to transform 1 dimension to 3 dimension. And now we will transform into a 3D box, particle in a box. And then we will actually change from box. So this is box. We will change it to spherical coordinate, because atom is better considered in a spherical form. Okay. So we will do later. Why we want to do that? Because we want to understand an hydrogen atom. Okay. So actually it's not like this. This is a previous Rutherford model, but for Bohr atom model atom is no longer like this. The model, right? Okay, so that's why we want to go step by step to understand lastly the hydrogen atom. So that is the first subtopic. So continue to the next video.